everyone thinks Mars is where we'll find life. For decades, it's been the dream, the red planet, the one we could terraform, colonize, make into a second home. Rovers, landers, sample return missions, billions of dollars poured into the red planet. We've invested our hopes there. But here's what NASA isn't telling you. The real candidates for life aren't on Mars at all. They're orbiting Jupiter and Saturn right now. 4 icy moons, Europa, Enceladus, Ganymede, and Titan, are far more likely to host life than Mars ever was. And the reason why will completely change how you think about where life can exist. Mars had its moment. Billions of years ago, liquid water flowed across its surface. Rivers carved valleys, lakes filled craters. Life could have emerged there. But then something catastrophic happened. Mars lost its magnetic field. Without that protective shield, the solar wind stripped away most of the atmosphere. And without atmosphere, water can't stay liquid. It either freezes solid or evaporates directly into space. That's the death sentence for life. In a cosmic blink, Mars went from a living world to a frozen, irradiated desert. The surface of Mars today is bombarded by radiation. Cosmic rays and solar particles hit the ground with no atmosphere to stop them. Any organic molecules exposed on the surface get destroyed. The evidence everyone talks about, the dried up riverbeds, the minerals that form in water, all of that tells us what Mars used to be, not what it is now. So what's left on Mars today? Trace amounts of briny water that might flow down crater walls during summer. But we're talking about muddy, salty seeps in an environment bathed in radiation. That's not a habitable environment. That's a planet that lost its chance at life billions of years ago. So, if Mars isn't the answer, where should we actually be looking? 4 moons in the outer solar system, Europa and Ganymede orbiting Jupiter, Enceladus and Titan orbiting Saturn. All 4 have liquid water oceans beneath thick shells of ice, but they're not equally likely to host life. Europa is the strongest candidate. Here's why. This moon shows overwhelming evidence for a global subsurface ocean that could contain twice as much water as all of Earth's oceans combined. Think about that for a second. More water than exists on our entire planet, hidden beneath a shell of ice. The ice shell covering that ocean is estimated to be 10 to 15 miles thick. Beneath it, an ocean potentially 40 to 100 miles deep. We've observed the surface flexing and cracking as Europa orbits Jupiter, exactly what you'd expect if liquid water is sloshing around underneath. Enceladus gave us something we never expected: direct proof. In 2005, the Cassini spacecraft was flying past Saturn's moon when it detected something impossible: massive plumes of water vapor erupting from cracks in the surface. These aren't small geysers. They shoot hundreds of miles into space. But here's what made scientists lose their minds. Cassini didn't just see the plumes, it flew directly through them. And what it found inside changed everything we thought we knew about where life could hide. The spacecraft detected water, salt, and organic molecules. Imagine being in that control room when the data came back. An ocean, actively venting into space. We didn't have to drill through ice or land on the surface. Enceladus is literally spraying its ocean into space for us to study. If this discovery fascinates you, drop a comment below. Which moon do you think is most likely to harbor life? And if you want to stay updated on the latest findings from Europa Clipper, we'll break down every major discovery as it happens. But what about the other two? Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It's the only moon with its own magnetic field, which tells us something about its interior structure. Scientists have confirmed that Ganymede has a saltwater ocean sandwiched between layers of ice. The ocean could be up to 60 miles deep, buried beneath 95 miles of ice and rock. That's a massive volume of liquid water in a stable environment. Titan is the odd one out because it has two potential habitats for life. There's a subsurface ocean of liquid water similar to the other three moons. But Titan also has lakes and seas of liquid methane and ethane on its surface. It's the only world besides Earth with stable liquid on its surface. The chemistry is completely different, hydrocarbon lakes instead of water. But it raises the question of whether life could use a different solvent entirely. All four moons have the same advantage Mars lost billions of years ago: stable liquid water protected from radiation. The thick ice shell acts as a radiation shield. The surface gets bombarded just like Mars, but anything living in the ocean below is protected. And these aren't frozen wastelands. They're active, dynamic worlds. Europa's surface shows evidence of recent geological activity. Enceladus is actively venting material into space. Ganymede's magnetic field indicates ongoing processes in its interior. Titan has weather, seasons, and an active methane cycle. These are environments where chemistry can happen, where energy flows, where the conditions for life exist right now. But Europa and Enceladus are where we're focusing our search first, and for good reason. They show the most direct evidence of active oceans and the chemical ingredients necessary for life. But how do these moons keep water liquid when they're billions of miles from the Sun? That's where the physics gets interesting. The core mechanism keeping these oceans liquid is tidal heating. It's a process driven entirely by gravity, and it's remarkably simple once you understand it. Think of it like repeatedly flexing a rubber band. Bend it back and forth enough times, and the rubber gets warm from the friction. That's essentially what's happening inside these moons, except the force doing the flexing is gravity from Jupiter and Saturn. Picture this. Europa orbits Jupiter in an elliptical path. As the moon moves closer to Jupiter, the planet's gravity pulls harder, stretching Europa slightly. As Europa moves farther away, that gravitational pull weakens and the moon relaxes back. This constant stretching and squeezing creates friction inside the moon. That friction generates heat, enough heat to keep a massive ocean liquid despite being 5 times farther from the Sun than Earth. And we have proof this is actually happening. Europa's surface shows cracks and ridges that only form when liquid water is moving beneath the ice. Enceladus is actively spraying water into space right now. These aren't theoretical predictions, they're observable facts. The same process happens at Enceladus and Titan with Saturn's gravity. Ganymede experiences tidal heating from Jupiter as well, though its larger size and different orbital dynamics create a more complex internal structure. The key point is that this energy source is stable and long-lasting. These moons have been heated this way for billions of years, and they'll continue to be heated for billions more. But this is where the story gets interesting, because it reveals why Mars failed and why these moons will succeed. Here's the critical difference. Mars had internal heat when it was young, generated by radioactive decay and leftover energy from its formation. But that heat ran out. The planet cooled. The core solidified. The magnetic field shut down. The protection for liquid water disappeared. Tidal heating doesn't work that way. It doesn't fade. As long as these moons orbit their parent planets, the gravitational flexing continues. Mars is a cautionary tale. These moons are the future. In 2030, we're about to get our first real answer. The Europa Clipper mission launched in October 2024, and when it arrives at Jupiter 6 years from now, it will do something we've never done before. Peer beneath the ice of an alien ocean. Nearly 50 flybys, radar that can see through miles of ice, instruments designed to measure how much the surface flexes during each orbit. We'll get precise measurements of the ice thickness, the ocean depth, and the heat flow. We'll know exactly how much energy is available for potential life. The data it sends back could answer one fundamental question. Is anyone home? So, here's the question you should be asking. If we got Mars so wrong, if we spent decades chasing a dead planet while the real candidates were hiding in plain sight, what else are we missing? The answer lies in understanding tidal heating. It's the mechanism that separates the dead worlds from the living ones. It's why Mars failed, and why Europa, Enceladus, Ganymede, and Titan will succeed. And it's the key to finding life anywhere in the universe. In 2030, Europa Clipper arrives at Jupiter. If we find life there, even microbial life, it means life isn't unique to Earth. It means the universe is teeming with it. And it means we've been asking the wrong questions all along. If you want to understand the right questions and be ready for the discoveries that are coming, subscribe now. We'll break down every major finding as it arrives. And if you want to understand tidal heating before the data arrives, watch the next video. It's the foundation for everything we've discussed here.